All right, well, I hope you enjoyed your snow day as I did on Tuesday. So I guess we're on the third of our multi-phase flow components. I realized in looking this morning at the quiz for 2.2 was a trip down memory lane. It was still the video for 2022, not 23. And so I saw myself wearing a mask, so that was a nice little revisit to that. So we're still talking about capillary behavior. It might be worthwhile doing a recap, perhaps that's a bit more in detail than before. Comments for the good of the order. Don't forget your assignments are due today. I did put on the syllabus today 10% off for each day late. I don't know whether we'll activate that. That only seems to be an issue. Was it last year or the year before? Some people kind of took advantage of it and it was days late. I'd imagine that since Shin is grading them, that as long as he gets it before he wants to grade it, that's probably okay. But you should check with him if that's the case. If you're going to be late, check with him. So we're recording. So what we have dealt with so far, actually, why don't I do that? It doesn't want to do that. If I do this, you've seen some of these things before. You've certainly seen this movie before, I'm guessing, 303. I should put it on looping, but I haven't. So this is kind of what we're talking about, multi-phase flow of the original components. The assignment that you're doing is the stuff dissolved in a flow, which is being carried downstream. So there's a bit of a disconnect maybe in the assignment and the class, because it's not about multi-phase flow. And so this is a movie by Ingrain, originally a startup company that was bought out by Halliburton. The idea is that they get the drill cuttings that come out of the drill hole. They CAT scan them to get the porosity. You can see kind of in the background these round spheres, which are an artificial porosity that they've just put this together rather than the real system. And they run numerical models that allow you to look at the flow of two fluids. So one fluid is the globs that you can see going through this. The second one is the transparent one. So you could imagine that this might be water displacing oil. The coloration is the pressures are graded from hot to cold as it goes from upstream to downstream, just like Darcy's law. And so if you capture all of the flow that comes out of the bottom part and look at it integrated over time and for steady state flow, you could potentially get a permeability out of the system, even though you've not run an experiment on it, because you've run a numerical experiment on it. So this is what we're looking at right now for our uses. There's a couple of different ones. I'm not sure, don't know what this is, but you've also seen this. Stuff upwelling from upstream. They've removed all the porosity, and this would be the fluid that's transiting through it. And I guess more relevant to us would be the final one here, which is fluid flow coming in from the top. So you spill something vertically, it travels being driven only by gravity. Gravity is the only force that's moving it. No substantial pressure gradient across the system, and it attempts to fill the void space that's there with the fluid that's there. And if maybe another fluid comes in, so I think a liquid is coming in that's traveling by gravity, and then for some reason that liquid is abating. Presumably that liquid is draining out the bottom and it's being replaced by more air that's coming to the system. So that's the system we're trying to talk about. And so if we repeat what we've said about this so far, then one discussion would be that to represent this system that we're trying to represent, so gravity flow into a system. You could imagine it occurring in a variety of different forms. We've talked about the fact that you get this chimney that forms It gets cupped by a capillary barrier that it can't get across. If there were lenses that acted as capillary barriers, they would be held in place as single-phase components. And depending maybe on the heterogeneity that you have in here, it gets some different architectures that result. These are all NAPLs, right? Because this is the water table, and they've transited to the water table. And then from our second class, which is on the Thursday, we had at least these representations of what's going on. And so the representation was that we could look at a capillary tube, the venometer, and we could get a height rise that would occur in that capillary tube, and we could define it in terms of the interfacial tension, the diameter of the tube, and the unit weight of the fluid. We didn't do it, although it was in the notes for that day. We could also look at a fracture being put in as two plates of glass in a liquid and see what the height rise in that would be. And we could show that the height rise would be basically the same expression, but with an aperture between the glass plates, replacing the diameter from before, and a 2 instead. And that we could write this height rise in terms of a capillary pressure, which is just by definition the difference between the wetting and non-wetting fluid pressures. And so by those, this is the wetting fluid. So this would be P wetting here, whatever the pressure you'd measure here. And P non-wetting, in this case, would be the pressure here, which would be the air. And the difference between these pressures is the curvature, severity of curvature of this is an index of how different they are. If it's very short radius and a very tight curve, then that means the pressure differential is larger. And we can define that capillary pressure differential as being equal to actually the HC multiplied by the unit weight of the fluids. It's a bit of a problem because you have to choose one of the fluids. And it would make sense to choose the water in this case, but that's not necessarily a given. And so capillary pressures are perhaps a better term to govern this behavior than height rise would be, because it's independent of the unit weight that you want to use. And so we could use these capillary models to understand what's going on. And we could use that then to say something about how fluid would travel in these capillaries. If it's a small capillary, it might get held and not allowed to advance. And if it's a bigger capillary, it might flow freely. And if those capillaries were in some kind of architecture that was big opening, then small opening, then you could imagine it getting a wetting fluid being hung up on the small gap in it and not being able to flow. And so it alluded to the fact that if you want to look at real rocks, then maybe these capillary models can give a sense of what's going on, but they might not be the whole story. And so the stuff we didn't talk about, which was stuff from Tuesday, was that we could perhaps represent the behavior by a very simple experiment. And the very simple experiment, if you looked at the notes, was to do this. So I won't go through it quickly, but I will say that what you could imagine doing is taking a core, having that core filled with something, maybe a non-wetting fluid, and you surround that core by another fluid, in this case, so the wetting, actually saturate the wetting fluid, which is water, and then surround it by oil, which is a NAPL. And so initially, this complete core is only got water in it. If you increase the pressure in the oil around here, what it will do is it will squeeze the oil slowly into the sample. And from what we know about the saturations, the pore space being finite, any amount of oil that you squeeze into it has to remove a portion of the other fluid. And that other fluid will go into this U-tube, which is the brine, which inhabits the fluid. And you can measure the amount that's expelled as a function of the capillary rise. And you'll get to do a question like this. I think it's going to be maybe the third assignment. If you imagine plotting the pressure that you apply to the non-wetting fluid, which is in the nitrogen, and which is in the oil, and if you have a pressure in the wetting fluid, then you can define the capillary pressure as being the difference between these. Non-wetting minus the wetting. And so in this case, the bigger pressure is going to be in the non-wetting fluid, right, to drive it in. And so what you will do, if this is saturation, I guess I always do this. I always say I'm going to just cover it, then I go into a full-thrown explanation. So if you imagine starting off the same pressures in these two, there's no invasion. If you increase the pressure, maybe you increase the pressure, you still don't get an invasion of the other fluid. You increase it some more, and at some magnitude, all of a sudden, you'll get the oil going into the fluid just like we've shown here. So it will slowly go in, and the saturation of water, which is 100% water is here, will become now a small portion of oil. If you then increase the pressure in the oil, you'll go up to this trajectory, and you will go across here. And so you immediately raise the pressure some amount, and nothing happens initially, but over time some more fluid infiltrates this sample, and you end up with another point. And so if you keep on doing that, you end up doing these things. If you draw the line that joins those together, then you have something that might be this, not a straight line, and then if you reverse it, you go down the same location. So in other words, you're stepping up here, and these are each of the pressures you get. And so we're only interested in the locus of these individual points. Because you raise the pressure, it takes a time for this infiltration to occur, and the time it takes for that to occur, you're increasing the saturation of the oil at the expense of the water. And so in each of these, again, this would be the saturation of the non-wetting fluid, and this would be the remaining saturation of water. That's all it is. Together they have to be 100% saturated. The sum of the two saturations is 100%. And this just represents that the saturation is changing. And so this is a useful way for us to think about this, both of when we're pushing oil into the system at the expense of water coming out of it, and when we're going down the reverse, when we're pulling oil out of the system and allowing water to replace it. So any place on this, so I guess if we continued doing this, what would it look like? We'd go down like this, and then it would readjust to this saturation. We'd drop the pressure in the oil again, and it would spontaneously suck water in, and it would go to these new saturations. So the point is that we can make these black curved lines. And these are called capillary pressure, not surprisingly, versus saturation curves. PC versus saturation curves. Sometimes called capillary pressure curves. And they tell us something about the motion of one fluid invading that space. And so that was kind of the topic of what we talked about last time. And again, I'm going to say too much about this. And the curves will look like this. And so these curves are made by doing exactly what we've explained or tried to explain. And these say something about the distribution of the two fluids in this. And the two fluids could be the oil that we're pushing in at the expense of the water, or you could think of us trying to push in air instead of water, which would also be a non-wetting fluid. It would cover both of them. And so for all of these, this is the trajectory that we go up, which is called a drainage curve. And it's called a drainage curve because these have been developed in agronomy, where by pushing air into the system, you're draining water out of them. And so this is where water is draining out of it. And so you note that this will always be just as we drew before. If you're at this point here, this will be the saturation of the non-wetting phase. So in this case, it looks like it's 35% or 0.35 saturated with air or oil. And it's, sorry, the opposite of that. It's from this to here, so it's 65%. And it looks like it's 35% water saturated. So the saturation of the wetting phase is equal to 35%. 0.35 plus 0.65 equals 1. So we satisfy what we said last time, is that the saturation of the two phases have to add up to 100%, either written as a percentage or as a fraction. And so this is an incredibly important curve for us to worry about, because it allows us to say how much of this non-wetting fluid is present in the system. And there are a couple of things. One is that if you drain fluid from it and you stop at some location, then if you reduce the capillary pressure again, so this is capillary pressure on this curve, then instead of going down this same curve, there's some hysteresis. And so you go across what these are called, they're called scanning curves, and it means that you get onto this other limb of the curve by going directly across it rather than going down here somehow. And so it matters what the previous wetting history is, and that's best explained by we mentioned it, I think, on the Thursday, that a raindrop on a windshield, if it's never been wetted before, then the contact angle is different from the trail that it leaves as it snakes down. And so the wetting characteristics on the already wetted part of the windshield is different from the virgin part, if you want to call it that. And so that's the reason for this hysteresis. If you skip from this drainage curve to the imbibition curve, and imbibition implies that if you drop the pressure, water is spontaneously sucked into it. It's imbibed, just like drinking, I suppose. Imbibition is drinking. And so this imbibition curve means that the water, because the grains like the water so much, they suck it back in automatically as the non-wetting phase is removed as a function of changing the capillary pressure. And so that's the reason for this structure. And the other characteristics are that if you remove all the non-wetting fluid, the NAPL or the air from the system, you never quite get back to 100% saturated. And that is because you leave some of that remaining phase present within the system. And so there are irreducible saturations. And we would have defined this as the irreducible saturation of the non-wetting phase. Irreducible, you can't get below that saturation. So it looks here that the irreducible saturation of the non-wetting phase is something like 15%, I would guess. And also, when you're pushing water into the system to push out the NAPL or the air, there's a percentage that is the irreducible saturation of the wetting phase. So SW0 here looks like 25%. And so those are the characteristics that we have to think about. And so in a way, they kind of describe the behavior that we talked about when we talked about saturations. So we talked about a lot of that last time. But we talked about this figure when we talked about saturations, and that was that for a water-wet sand, we have water as a monolayer all around the grains, but also this pendular saturation, which is a donut, which goes around two contacting grains. And so it means that at any particular pressure that we've applied to get the saturation to look like this, there's both non-wetting and wetting fluid in there. And that's not something that we really get out of it if we look only at a capillary model, which includes just a single capillary, right? We need a better description. And so this better description is given by these capillary pressure versus saturation curves, which we'll use quite a lot in this class. So if you understand the components of that, you're already partway there in terms of understanding everything we need to understand. And of course, the real system for that is a bit like this, which we also looked at, right? So this is a NAPL that's displaced water. So it's only saturated with water in this plate. Where the NAPL is invaded, if we took a little cube out of this and looked at the relative proportions, you can't really see it here, but the mostly red fluid would suggest that the NAPL is 95% filling the space, but there would still be some water in here. And so when we take not a model of just the capillary tubes or the pores only, where we include the saturation as well, the solid grains as well, we write the saturations only in the void space, and the void space is 95% filled with NAPL and 5% water, because the water hasn't been pushed out. If we did the same thing down here and looked at a little part of this ganglion, perhaps that would be in these same proportions. This, I guess, would be 100% water and 0% NAPL, because it hasn't got there yet. And we can think about these as being different proportions. And so what we've now done with that diagram is that we've kind of related these joint saturations to some magnitude of another property that controls that, and that is that we know something about the capillary pressure that would be present at this point as well, because in this diagram that we have here, we've said that every saturation that exists here belongs to a given capillary pressure. And the most important of these capillary pressures, the king of capillary pressures if you like, would be something that we'd have described last time as the bubbling pressure, which we also called PC0. Capillary pressure at zero saturation of the wetting phase. So in other words, it's the pressure you have to apply to squeeze the first bit of water into this NAPL oil saturated system that hasn't seen water before. And that's important because then all of a sudden it's not 100% NAPL saturated, but it's 99.999% NAPL and 0.001% of water. So the other thing that relates to, again, and if you understand this diagram in relation to this, and this was talked about last time, is that this is the capillary pressure curve we just drew. It's only got one limb on it because we're ignoring the other limb that would come down and look like this, just because it's easier to draw the figure. And this represents, again, the saturation in the non-wetting fluid as a ratio of this length, and the saturation in the wetting fluid. And so this is drawn this way particularly. So this is the water table. So this is sitting below the ground level. This is the water table here. The water table by definition has a pressure of 0, atmospheric pressure. That's the definition of the water table. It has the capillary saturated zone above it, but the water table by definition is a gauge pressure of 0. And so if you think about what we know about how pressures change with depth in a swimming pool, if you go down in a swimming pool to some depth, the pressure will build linearly, so that at some depth below the water table, it will build, so the pressure is equal to the unit weight of the water times the depth below that surface. We know this. And so the other fluid in this is going to be air, and this is going to be water. And so below the water table, it will build as depth times unit weight of water. But also, as you go up, if it still has water in it, if you go up in the water film that's present in this, then you'll find also as you go up that the pressures will be the opposite of that. They'll be exactly mirroring this, but negative. So this is a negative value, which will be the water pressure is equal to the unit weight of water times Z. Z has a direction to it, right? Above the water table, going upwards is increasingly negative. So this will be a negative pressure. That's a PW. And so this is why it's called a tension saturated zone or capillary zone, is because it's in tension. Because you're physically pulling this water up when you're sitting at this point, and the amount of pressure you have to apply to pull it up is equal to this kind of tensile stress. The air in this, if it's connected to the surface, also has a unit weight attached to it, but the pressure of the air, which is also the non-wetting fluid pressure, is going to be equal to the unit weight of air times its elevation. But because the unit weight of air is 1 kilogram per cubic meter out of 1,000, it's essentially parallel to this line. So this magnitude here, the difference between the green curve and the blue curve, is by definition the capillary pressure. Right? This here. And it's this capillary pressure which is increasing as we go up. The non-wetting is subtracted from it. And it describes exactly how, as we go up in the vadose zone, it's almost fully saturated with water until we get to this location here. And as we go up here, so this would be 100% water saturated. And because it's not allowed, it's not above the bubbling pressure. This is what we call PC0. And as soon as we go above this bubbling pressure, all of a sudden air can invade if we're doing this experiment. And so we're not doing this experiment by changing PC and going up this curve and making these other curves, but elevation within the soil is doing that for us. And so the capillary pressure curve defines the distribution of saturations. And each of these saturations, if you like, the combination of them has a unique capillary pressure attached to it. And so we can describe this behavior in the vadose zone in terms of this capillary pressure curve. The other thing we can do is that we can also turn the curve upside down and look at what it would look like if we have the groundwater surface here, it's saturated to the water surface, and we play the same game. So we go down from the water surface, which we're going to call the water table. If it's water, it will increase as the unit weight of water. If there's a fluid within there which is denser than water, then the pressure will build faster as a result of that. And so if you look at this green fluid being a continuous phase as you go down from the ground surface down, the pressure will build so that at this particular depth here, the pressure will be this amount. And in the blue fluid outside of here, the pressure will only be this amount. And so again, by definition, the capillary pressure will be the difference between those. So it's just the difference between the green curve and the blue curve. And so we can play the same game as we go down with the capillary pressure curve. As you go from here, the capillary pressure is 0. And as you increase, it will increase linearly as the difference between the green and the blue curve. So the capillary pressure is increasing as you go down here. And so we just flip this diagram upside down. And so as we go down, this will be at this capillary pressure here. This will be 100% water. This also is the saturation of the wetting phase. This is the saturation of the non-wetting phase, the NAPL, which increases as we go down because it's able to invade. And of course, you can link this capillary pressure directly to which is the same as the depth of the non-wetting fluid minus the depth of the wetting fluid. Just from the definition of a pressure as being, as this value here, right? This is definition of pressure. And so which I guess you could also write as being the depth multiplied by the difference in the unit weights. And so if you know the difference between these unit weights and you know how deep you're going, all to say that this capillary pressure also scales with depth in some way. And so this is kind of useful to us because we can say something about how saturations vary with depth. And we can say something about how much pressure we have to apply to be able to invade it with the NAPL in the first place. It's a physical property of the medium and the fluids that are invading it, and we'll get that from an experiment. But this is what it would look like in that particular arrangement. So that was what we did talk about last time. It's a useful curve to talk about because it's pretty fundamental to what we're doing. So if you understand what we said about the form of this curve and how we get it, and if you understand why this capillary pressure versus saturation curve sits in these two different configurations, for the vadose zone above the water table and for invasion by oil denser than water going down from the water table, then you understand pretty much all you need to know about this multiphase fluid part of the class, at least until today. Okay? So that's that. So, what else? If you looked at these figures, so these figures say, so we need something, a better description other than these capillary models to say something about what's going on here. If we know what the relative saturations of the red NAPL and the water and the air in this zone are, we'd know exactly what the capillary pressures would be along this trend. We could imagine perhaps that this chimney is a smear of a NAPL, left portions of which are in the system. We talked about the idea that we could have a capillary barrier where if the pore throats were small enough, then it wouldn't let the stuff pass, even if you apply a very big pressure on it to try and push it through. And I guess the other question we can ask is, if a capillary barrier isn't there, how deep will these fluids penetrate? Will they keep on going on, or will they actually arrest at some stage? So that's the one thing that I was going to talk about today. So that follows from here. And so you can do a little thought exercise. Back to where we were with this. Go around. This is all from... Is this from last year? So it's a different one? Yeah, it's not the one from this year. Last year's stuff. So here's the thought exercise. So if you ask yourself a question, how deep can it go? And so we can do this thought exercise. We know that we describe this bubbling pressure, which is a pressure that you have to apply in water to get it to push out oil, or a pressure you have to apply to a water-saturated medium to get air into it. And that physically has a magnitude which is a function of the porous medium. So it's a physical magnitude. So we can ignore that for a moment, and we could think about a system where we have a non-wetting fluid and a wetting fluid in a swimming pool. And in this particular case, we know that if the non-wetting fluid is lighter than water, it would sit on top of the water, which is fine. And that's no problem. And what would happen if we then take that non-wetting fluid, which is sitting on top of the water, and we pull it down a small amount? It's called a perturbation analysis. And so if you look at the pressure that would exactly act at this point, we can calculate the interface. In the non-wetting fluid, it would be equal to the unit weight of this fluid multiplied by its depth, which is this. Original depth plus a small increment. But the pressure acting upwards is going to be equal to the pressure in the water acting at this depth, which would be equal to the unit weight of the, well, it's going to be equal to what? It's going to be equal to the unit weight of the non-wetting fluid pushing down, and equal to this amount of, so you know that as you go across horizontally in a fluid, the pressures all have to be the same. So you can get the pressure at this point by looking at the height of this non-wetting fluid plus the height of the water. Height of the non-wetting fluid times its height plus the depth in the water. And this is the pressure that's acting upwards. And if this pressure is larger than the red pressure, it will re-establish the equilibrium. If the pressure acting downwards is but larger than the blue pressure acting upwards, then this little blip will tend to glow, and it'll be like a lava lamp, and it will move down. So if the non-wetting fluid density is more dense than the water, then you can show from this that the pressure acting downwards is going to be larger than the pressure acting upwards, because a portion of the pressure acting upwards is just the unit weight of the water acting upwards, which is less than this unit weight. You can just do the math. And so that's the rationale of why you can't have a denser fluid settling a less dense fluid. In theory, there's no reason not, because if there isn't this perturbation, they'll just sit happily there, because the fluid acting on this surface, if there isn't this little blip, are going to be in equilibrium. But if this blip occurs, then this will grow, and it'll just get deeper and deeper and deeper. And then maybe it'll detach as a bubble, like a lava lamp. And so we can do the same analysis if instead of having a swimming pool, we have a porous medium, and we have a height of the non-wetting fluid that acts here. But now maybe we have to think about the fact that if it's a porous medium, we have to apply a big enough pressure to be able to overcome the resistance to pushing it between the grains into our porous medium. And so that's the only difference that we have in this particular case. And so if we do that, we can do the same analysis. So this same thing that we have here would look a bit like this. This red thing would be the ganglion of this non-wetting fluid, which goes down to this depth. And again, we can look at the pressure balance between the column of the red with the blue on the outside, a bit like this picture. So the red fluid on the inside and the water around it. So we're looking at the pressure at this particular location here. And we can do the same kind of analysis. And if we looked at what those pressures would be, then the pressure in the non-wetting fluid acting downwards will stop if the pressure in the water acting upwards plus the barrier to get it into the porous medium in the first place. This barrier pressure here is the excess pressure we have to push it in between the grains, so that we're not in a swimming pool anymore, so we have that additional component to add. And so we have to overcome this small entry pressure. And so if we do the math to put this together, which I won't do, we can show that the minimum height that we have to get to is equal to some material property. This is a function of the entry pressure. So I guess PC0 is equal to the unit weight of the non-wetting fluid times the height of that fluid, right? Just by what we said before. It's a property of the medium and the ratio of the two unit weights. So that's what we end up with. So all it's saying is that as long as this height is big enough, then the pressure acting at the base will be big enough to overcome the pressure of the water acting upwards and the entry pressure which is acting against it. And so this is the criterion, if you like, to say when it is that the red fluid will keep on going. If the height of this red fluid is less than that, then it doesn't have enough pressure acting at the tip to be able to move. So the implications of that are that it has to be this length to be able to invade. But I guess also the other thought experiment is if it's that long and it can invade, then so long as it's longer than this minimum height, then it will just keep on going. So it doesn't need to be resupplied with stuff, but if it's long enough, then it will keep on invading at the bottom, and it will keep on merrily going down until it reaches a capillary barrier which would stop it. And if it met that capillary barrier, it would pond on top of it and become this lens, but absent that, it won't stop. But the only way it will stop is that if you imagine it necks down, so it breaks, and that each of these limbs is now less than this minimum height requirement, then it doesn't have enough pressure acting to be able to move. And so as a consequence of what we know about these capillary pressure versus saturation curves, this entry pressure, we can say something about what controls the migration in the subsurface. And it merely says that if it's a big enough height to be able to invade the space, then it can keep on going. But the countering argument to this is that if you look at this geometry, say this is a 55-gallon drum that's sitting on the surface, and the water table is present at the surface, we know that the pressure here is atmospheric, and we know that the height of this is enough to be able to overcome this atmospheric pressure. So for this geometry, if we calculated the height that we have to invade the porous medium, we'd come up with just the fact that this height has to be equal to the entry pressure, because the pressure due to the water isn't there because it's on the surface. So we actually kind of have two results. One says that if the height of the NAPL is equal to h sub c, a function of our porous medium, then it will invade in this geometry. But if the NAPL is already in the subsurface, then the height for it to invade is different from that. It's h sub c divided through by this factor. The unit weight of the non-wetting fluid, if it's a DNAPL, always has to be bigger than this, so this number has to be less than 1. So this number has to be overall less than 1. So this minimum height has to be bigger than hc. It's less than 1 in the denominator, and so this has to be bigger than hc. So how do we resolve that conflict? And so the conflict is just this. And so in one, we have a ground surface with a water table on it and a 55-gallon drum on top of it, and no water out here. In the other, we have the groundwater surface is here. We have the NAPL already below the groundwater surface, and this value is different. So why is that different? Well, the reason is because in this case you have air out here, and here you have water. And so all this is that the buoyant force of this DNAPL is affected by the fact that the buoyant force in water, it's displaced this amount of water. Water has a bigger density, and so it pushes back more, and therefore this has less. This has more. The effective force of this acting downwards is less in this particular case because it's got the buoyant force of water acting around it. That's really what's going on. And so these seemingly contradictory results, where the minimum value here is HC divided by a factor less than 1, and this result here where it's HC divided by 1, they seem to not make sense, but they are because they're representing different circumstances. And so we should be mindful of that. So we should be aware of that. So that's that. What else do you want to talk about? I don't think we have anything else to talk about today. So we've got through that very, very quickly. Oops, didn't mean to do that. So that's about it. So I think the key figure in this, which synthesizes all of this stuff together, is this figure here, which merely allows us to take these capillary pressure diagrams that represent these static systems. So these have clearly, to get into this configuration, it must have migrated over time. So this is after that time has occurred and it's reached some equilibrium and it's held in by these interfacial tension forces, and they're very difficult to move against those forces. So this is held in some kind of temporary equilibrium until the system's re-perturbed. It allows us to be able, if we have this property curve, it's a function of the porous medium and the fluids that are saturating it. If we know exactly what these curves are, then we can say something about the distribution with depth in the vadose zone for these air-water systems, and below the water table for these water NAPL systems. And the saturations have to conform to the depth distribution according to the capillary pressure magnitudes. If we know what the difference between the pressures are at any point, as in the definition of the capillary pressures is just the difference in pressure between the blue and the green curves, either below the water table or above the water table, then that allows us to scale vertically. And if we can scale vertically, we can get the saturations with depth. And we can also determine what the height of the column of fluid would have to be before we invade it. And the last, perhaps, thing to mention, since we have 5 minutes, which I think is another key feature, is that these capillary pressure versus saturation curves we can think of as looking, do I not have one here? As looking like the curve we have, but we can also write them in a non-dimensional way. And this is the same curve that we had before. This is capillary pressure on the vertical axis. This would be a bubbling pressure. If you exceed the bubbling pressure, you drain the water out of it as you invade with the other fluid, which might be air or the NAPL. If you turn it around, you have hysteresis and you go back down here. But this curve has an interesting axis. The axis is actually not capillary pressure. It's called a Leverett function, which is this parameter J, which is capillary pressure divided by interfacial tension and multiplied by permeability and porosity to the power of a half. And capillary pressure has units of stress or pressure. Interfacial tension has newtons per meter, because it's a force per length around the capillary, as we noted. Permeability, so this is, if I write these out, hopefully it works out. This is in newtons per meter. This is in newtons per meter squared, as all pressures. Porosity has no units, and permeability, which you haven't really talked about yet, has units of meters squared. So hopefully if we put these together dimensionally, we have newtons per meters squared for this. We have newtons per meter for this. We have permeability, which is meters squared to the square root. And so if you look at what the dimensions of this J function are, is it has no dimensions. Newtons cancel out, Newton meters squared per meter squared. This is a square root of meter squared. And so that cancels out as well. And so another application of non-dimensional numbers like Buckingham pi is that this analysis, which we won't talk about now, gives a value of this J function for the bubbling pressure is equal to 0.3, roughly. This is 0.2, this is 0.3. So if you write this out as capillary pressure over surface tension, permeability and porosity to the power half, this is the capillary pressure. Then very specifically at this very important capillary pressure here, which is our capillary pressure at which the porous medium gets invaded, this at PC0 is equal to 0.3. Yeah, maybe in a later week we'll talk about where this comes from. It's actually quite a simple analysis. But the utility of this is that this is always kind of true. And so typically we'd want to know what this number is, and it's not a very easy number to get. It's a very unusual number to take a sample from the field to the lab to get this. But we could estimate that if we know what the interfacial tension is of the fluid, get that out of standard text, if we know what the porosity of our porous medium is, and if we knew what the permeability of our porous medium is. Because we know it equals 0.3, and the only number we have in this term here is the capillary pressure. Everything else we know. And so another utility of this is to be able to get the bubbling pressure out of this as a function of this characterization, which we can do if we know all of these other terms. And if we know the bubbling pressure, we immediately know something about where this curve is anchored. And if we know where this curve is anchored, then we know this, and we can say something about what happens in the subsurface in terms of invasion at very low saturations. And so I guess really one of the problems with DNAPLs, it's alluded to here, is that saturation can occur, invasion can occur at very low saturations. And so here in this whole chimney, you'd imagine that it might be 80% filled with air. It probably has some water in it, maybe at 10%, and maybe it has a smear of DNAPL also at 10%. So you started off with the DNAPL at 100% concentration in this 55-gallon drum. If you wanted to remediate that, that's easy. You find a barrel, you take the barrel out, it's all there, it's gone. Once you've spread it around and smeared it all the way through here, now you have to recover it at very low concentrations, spread through a huge volume, pooled maybe in some areas, but you have to remediate this at very low saturation, and you have to find some ingenious way to be able to access this big volume. So it's like spilling a bunch of tacks on the floor. It's great when you have them in your thumbtack container. If you want to stay safe, you have them there. Once you've spilled them on the floor, they're distributed all over the place, and cleaning them up is perhaps no mean feat. So that's it. So we've kind of, we're in good shape. And I don't really have much else to chat about. Shall we stay and chat? I can't believe that you... was going to say, I can't believe that you don't smile at this stuff, but maybe you just don't find the humor very engaging. So I'm fine with that as well. Anything you don't understand from today?